going to quickly review the definition of functions. Anybody remember what it means to be a function? No? You have talked about functions in the past, though, right? Okay. So, in its most basic form, a function involves two sets. The first set we call the domain, and the second set we call the range. And a function is just some sort of rule that assigns elements of the domain to elements of the range. For instance, we could say the domain of this classroom is all of the students. So if we listed all the students, and the range of this function would be all of the cities that the students live in. So Dylan lives in Castledale. Kelsey, where do you live? So Kelsey lives in Clawson. Katie, where do you live? So we'll Katie that way. Huntington. Okay. Anybody else live in Castledale? Huntington? Oh, Laura does. Okay. So Laura, she lives in Castledale. Anybody else in one of those other cities? Nobody else lives in Huntington? Okay. So Micah lives in Huntington, and Jed also lives in Huntington. Now, we could set this up for the entire class. This represents a function. Okay? Functions only need to follow one guideline. As long as they pass that one guideline, they're considered a function. That guideline is for every, wow, that's a cool word. For every part of the domain, so of capital D, there is only one part of the range. Which means, whenever you look at something in that first bubble in the domain, and you're drawing lines, everything in the domain only has one line, which in this case is always going to happen. Is it possible for one person to live in two different cities? Not at the same time. I mean, on Tuesday you might live in Castledale, and on Wednesday you might live in Farron. But at one time, you're only living in one city. Now, what if you lived on the border and the line cut your bed in half? Well, you can't be entirely within two cities at once. So we would pick the bigger half and say you live in that city. Okay? So is it okay that Dylan and Laura both live in Castledale? Yes. Functions don't say anything about that. All it says is, if you give me a person, they're only allowed to live in one city. What if everybody in this room lived in Huntington? I mean, other than the fact that who wants to do that? Would it still be a function if everybody lived in Huntington? Yes. The trouble you run into, let's say we had person 1 and 2 and 3. Is that a function? No. Why not? Person 2 apparently is living in city 1 and city 3 at the same time. That breaks the rules. Is it okay for persons 2 and 3 to be in city number 3? Yes, that's totally fine. This is okay. The trouble is when we connect the 2 to both the 1 and the 3. So in math, we can write a function as a list of ordered pairs, as x's and y's. So if I had an xy column, and I had 4, 8, 6, 9, 2, 1, 3, 8, negative 4, 2, 8, 6, 1. Is that a function? Yes. 4 goes to 8 every time. 6 goes to negative 4 every time. What would I have to do to break the function rule? So let's say that in addition to 4, 8, I had 4, 6. That breaks the rule. Okay. What if everything on the right side was a 7? That's all right. Okay. So let's graph something that's not a function and see if we can determine what it is about a graph that makes it not a function. So here I have this nifty grid. We'll graph 2, comma 3, 4, comma 1, 6, comma negative 2. So 2, 3, 4, 1, 6, negative 2. Is that a function? Yes, it is. What would I have to do to break the function rule? I could pick any one of these x's, so 2, comma, anything other than 3. What if I did put a 3 there? Is that still a function? Yeah, because it's just graphing that same dot over and over. And as long as it always remains in the same place, it's still a function. So instead of a 3, what if I put a 6? So 2, comma 6. Now, there is a visual key here that we need to understand. What is it about these 2 points that tells us the graph is not a function? They're vertical from each other. The reason that's the case is this first one is 2, comma 3, and the second one is 2, comma 6. And whenever you have two x's that are the same, those points are going to be one on top of another. Okay? Well, we can extend this idea of functions into equations. So if I had the function f of x is 2x plus 1, I can turn that into an infinite number of points. One really slow way to do that is like this. So I build the table 0, 1, 2, 3, 0, comma 0 plus 1 is 1. If I plug in 1, 2 times 1 is 2 plus 1 is 3. Plug in 2, 5, I'm seeing a pattern. 7 and 4 would be 9 and so on. Okay, how long is it going to take me to write down all the numbers? I'll never get there. In fact, infinity is so big you can never even get close to it. So I'm no closer now than I was when I started. So if you're trying to count to infinity, you might as well stop now. Because even if you count for 100 years, you're not any closer to infinity than you were when you began. Kind of depressing, huh? Okay? So one way to represent all of the points is to graph them. So I have 0, 1, 1, 3, 2, 5, and so on. Is that all? I could draw a line. And this line is going to go forever in both directions. Okay? If I were to look at the domain of this function, are there any x's I'm not allowed to plug in? I can plug them all in. Okay? Are there any y's that will not show up on that right side? They're all going to show up, and that's what we're going to do today. We're going to try to decide how big the domain and the range of functions is. Okay? Now, does this graph represent a function? Can we look at the graph and say, yes, it's a function? How come? There are no vertical points. Good. So what if I graphed a circle? Is that a function? Why not? Can I find two x's that are right on top of each other? Yep, right there. We call that the vertical line test. If something passes the vertical line test, meaning you can draw vertical lines and they always hit either never or once, then that's a function. But as soon as it starts hitting more than once, not a function. Okay? So what if I graphed a smiley face? Is that a function? No. Well, how many times does that hit? Once. It only hits once. That's okay, right? So it's a function. No. How come? Because there is a point right there that does hit twice. You wish you could do that on your paper, huh? Well, if you really want to have fun, you can do this. Oops. Okay. So the vertical line test is half of what you're going to do on your worksheet today. You're going to say, is it a function, is it not a function, using the vertical line test. So let's look at another one. Is that a function? So let's do my vertical line test. So I'm going to move this across and tell me if I hit the graph twice. Ooh, right there. I hit the graph twice, which means not a function. Okay? So are there some graphs where you're not allowed to plug in certain x values? Can you think of an equation where you're not allowed to plug in, say, 7? They do exist. Let me show you one. So that would be the y values. So we will get into that. We're going to look at the x values. Let's consider the function g of x equals 1 over x minus 3. Okay. Are there any x's I'm not allowed to plug in? Well, let's try a couple. So x, y, let's plug in 1. What happens when we plug in 1? Negative 1/2. Okay. What happens when we plug in 2? One over 2 minus 3, which is negative 1 over 1, which is just 1. Okay? What happens when we plug in 3? Careful. We get 1 divided by 0, which equals, try that on your calculator. Error. It gives you an error. Now, nobody's ever bothered to tell you why it gives you an error. So you guys like the word undefined because that's what your teachers have taught you in the past, but they never bothered to tell you why undefined is not good. You probably just forgot. Okay. Now I got my calculator on. So if you end up with 1 divided by 0, it says, haha, yeah, right. I don't divide by 0. Right? Why not? What's wrong with dividing by 0? Nothing, meaning so you're looking at it as, what is 6 divided by 2? It's 3. The reason it's 3 is because 2 times 3 is 6. That's what you're saying, right? So if I asked you, what is 6 over 3? The answer is 2. The reason it's 2 is because 2 times 3 is 6. So if we apply that logic, 1 over 0 equals something, which means that something times 0 must be 1. Well, that's a problem, right? What is something times 0? Not all the time. But good, Teres. I'm really impressed. That that is really good logic. Now, the number I'm looking for is one you've never dealt with before. No, it's not I. Nice try. You have dealt with i's before. So, I mean, that's a really good way to look at it. We have been taught that everything times 0 is 0. But we're looking for a number times 0 that equals 1. Yes, sometimes. Okay, so let's consider it. Let's consider 1 divided by 1 is 1. Oops. 1 divided by 1 is 1. Let's make the bottom of that fraction smaller. So I'm going to do 1 divided by something. So let's change it to 1 divided by 0.5 is 2. Why is that the case? Because 0.5 times 2 is 1. How many 0.5s are there in 1? 2. Okay? So 1 divided by 0.1 should be 10. All right? So let's take this number and let's make it as small as possible. Well, we want to get it as close to 0 as possible. Okay? So 1 divided by 0.01 should be 100. 1 divided by 0.001 should be 1,000. Okay? So let's call this A, and let's say that this equals B, which means A times B equals 1. Okay? Now, as A goes down, then B goes up. Everybody agree? So you'll notice every time I make A smaller, B gets bigger. Well, let's do 1 divided by 0.00001. What does that mean? 1 times 10 to the 14th, which is huge. Okay? 1 divided by point. Let's really make the calculator mad. Okay, lots of zeros. Wait till it stops blinking. Okay. Yeah, right. It says, nice try. Oh, did I? I forgot my 1. Sorry. Actually, let's do this. Let's do second, enter, 1. There we go. So I pushed 41 zeros. Okay? Now the calculator can only handle 100 zeros. What's going to happen after I hit 100 zeros? The calculator is going to say error because it's not going to, well, I guess technically it's close enough to 0. But why is the calculator going to give up after I plug in 100 zeros? It can't do what? So the answer would actually be, what's wrong with that answer if I put 100 zeros in there? It's too big, right? Okay, so if we look over here, as A goes down, as the denominator of that fraction goes down, B goes up. Well, if I were to put 100 zeros, A is so small that B would be too big for the calculator. What if I were to put an infinite number of zeros? What is that answer if I have an infinite number of zeros? And then a 1. What would A be? 0. Right? If I had 0.00, an infinite number, 001, well, that number doesn't really exist, right? But if it did, it's actually equal to 0. Because if you put an infinite number of zeros, you never get to put the 1. Because you'll never reach it. So what the calculator is telling me is, if I try to divide by 0, as A approaches 0, B is approaching So your calculator says 1 divided by 0, nice try. I'm not going to tell you the answer because I don't have that much memory to tell you. 1 divided by 0 is infinity. So if we go back to this, 0 times infinity, now sometimes, that's not always true. Sometimes it's, well, it kind of depends on how big your infinity is. That's true. Not not all infinities are created equal. Some are bigger than others. So in calculus, we do math with infinity all the time, and it's really fun. Right? How about this one? Now, here's where the problem comes in. Not necessarily. So in calculus, you will actually run into infinity minus infinity all the time. But the trouble is some infinities are larger than others. Well, the crazy thing about this is sometimes the answer is infinity, if this is the big one. But if they're the same size, what's the answer going to be? 0. Well, we'll get to that. So what if this one is bigger? Negative infinity. So whenever we have infinity minus infinity, we say, I don't know. But a lot of times there are other ways to figure it out. Little tricks that we've learned that will usually tell us one way or the other. Another problem we have is infinity times 0. Sometimes it's 0, sometimes it's 1, and sometimes it's infinity. Yeah. Well, guess what? You don't need to know that in this class. Okay? But let's go back. Let me find that. Well, I don't remember where it went. So we were looking at 1 over x minus 3. And we plugged in the number 3, and we ended up with infinity. So we had 1 comma negative 1/3, 2 comma negative 1/2, 3 comma infinity. Well, that's a problem. Okay? Well, infinity is not a real number. I don't mean that it's pretend. By real number, I mean number on the number line. Okay? In order to be a real number, you need to be able to put a mark on the number line and say it's right there. Infinity is off the number line because it's so big we can never nail it down. As soon as you get to infinity, it just goes out further and you miss it. Yeah, it never stops. So what we say is, here is a person that doesn't really live in a city. Okay? So does anybody live in Outer Elmo? No, Outer Elmo? Climo? Whatever. So, anybody live near Lawrence but outside of Lawrence? Do you actually live in the city? So, if we had a function of all the students in this room and we put the cities they live in, Jed doesn't belong. Right? Jed is infinity. Well, but there are other reasons why you might not belong. You might be an imaginary number, so he could very well be an imaginary number. So if we built this function with my domain and my range, and I put Jed in here, and I went to make a line, what line would he attach to? None of them. Which means Jed does not belong to this function. So what we do is we just go and we erase Jed. But he could also be I. There are other ways to be excluded than just infinity. So does that make sense? Jed exists, but he is not part of this function because he doesn't live in a city. What's that? Odd? Square rooting negative numbers. Or you could just set a rule and saying all of the even numbers don't belong. You just state it that way. Okay? So, Jed does not belong to this function. Now, there are several ways to not belong, but we're going to look at functions and determine what x values belong and which y values belong, which is essentially saying, of all the kids in the class, which one of them live in cities? And those of you that live in cities would be part of the domain. If we looked at all the cities in the United States, are all of those cities represented by people in the class? No, we might have maybe a dozen or so. Does that make sense? So of all the cities in the United States, only 12 of them apply to this class. So we throw Jed out, because he doesn't live in a city, and that we call everybody else the domain. Then we look at all the cities in the world, and we throw all of the cities out except the ones that you guys live in, and we call that the range. So let's look at a graph. Okay? So here's a function of x's and y's. First of all, is this a function? Yes, it passes the vertical line test. Okay? Now, I want to know of in the domain which x's belong. Now, this is a little bit tricky. We're going to look at the x-axis. Okay? There's my x-axis. Let's pick a random number, -3. Does -3 appear on the graph? Where do I find that value? Straight above it. So it's right here, -3, 4. So, person -3 lives in city 4. Does -6 live in a city? Where's that one? It's going to be way up here. Okay? Good question. This is curved. Is it ever going to eventually curve straight up? That never happens. Okay? If it appears that something is starting to go straight up or straight down, just trust me, it will never happen. Unless it curves back. So if it curved and then cut back a little bit, but then it's not a function, and if it's not a function, it will be stated on the graph. So you can assume that because this is an arrow, it's going to continue in function fashion. Okay? It will never curve back on itself unless it's part of the visual portion of that graph. Okay? Now, it might get super steep, but it will always be inching its way over a little bit. It might take a while, but eventually it's going to continue to go over. Okay? So, of all the x values out there, are there any that miss the graph? That hits, that hits, that hits. So the domain is x equals every real number. Okay? So now we'll state the range. Oops. The range is the y values. Are there any y values that are not represented on the graph? So let me get rid of some of this stuff. Oops. So let's look at the y values. Now I can draw a line here, and I can move that. Oops. Move the line. Does this line miss the graph ever? Where does it miss the graph? From here down. Okay? Then from here up, it hits the graph. So I'm going to teach you what is called interval notation, which is a little bit tricky. In interval notation, you write the smallest number it hits and the biggest number it hits. So this red line, what is the smallest y value that this red line hits? 1. What's the biggest one? Infinity. So I write y equals 3, y equals 1 comma infinity. Now, do you remember when you did these a long time ago? And there was a difference between this and this. The bottom one was x is greater than -5, and the top one was x was greater than or equal to -5. The same rules apply here. Okay? We're going to put parentheses around our interval. So I'm going to put either parentheses or brackets around the interval. Now this does not mean x comma y. This just means y is every number from 1 to infinity. Brackets mean equal to. They're called a closed interval. And parentheses mean not equal to, and it's called an open interval. So, is 1 part of my range? Yes. So it gets a closed bracket, which means equal to. Now, is infinity part of my range? No, I can't actually get there. Every number up to infinity counts, but infinity does not. So infinity gets an open parenthesis. Now, don't get this confused with x comma y. This is just saying the domain is every x in the real number set. The range is every y from 1, including 1, all the way up to infinity. Okay, let's try another one. So that open circle means we miss that point, and the closed circle means we include that point. Okay, first off, is this a function? Yes, it passes the vertical line test. The vertical line test says, I draw a vertical line. Does that vertical line ever hit twice? No. So we're okay. So it is a function. Now let's look at the domain. So I'm going to draw, this is my x-axis. So I'm going to take a vertical line that touches my x-axis, and I'm going to move that across. Are there any of these lines that miss the graph? Yes. So some of them miss. What's the smallest one that hits the graph? -4. Well, and we'll just use an open, so it's like -3.999999999. Well, that's no fun. So we'll just say x equals -4. And what is the biggest number that hits that graph? 3. Now, is -3 part of the set? -4, sorry. Is -4 part of the set? No. Open. Okay? And 3 is part of the set, so it's closed. Okay? Now, we flip this, and we make a line that hits the y-axis. Are there any of those y values that miss the graph? Yes. Okay, so what's the smallest one that hits? Right here at -1. So the range, x equals -1. all the way up to, we bring this up to 5. Does -1 count? No. So open. Does 5 count? Yes. Closed. Okay, let's try another one. Okay. That is not a function. It fails the vertical line test. It still has a domain and range. Okay, so you just write not a function. Okay? This is not a function because it fails the vertical line test. Okay, are there any x's that miss? So you draw a line that goes through the x-axis. Are there any x values that do not hit this line? Except, and that's it right there. So this one misses. So there are two ways to write this. We could either say the domain is x equals, what's the smallest number on the left side? -infinity, goes all the way up to 3. Is infinity included? No. Is 3 included? No. Now there's another set. What's the smallest set on this section? 3 is the small number. The big number? Infinity. Does 3 count? No. Does infinity count? No. That's one way to do it. The other way is, how many numbers did I skip over? Just one. So you could also say x equals the real numbers, comma, x cannot equal 3. And that works too. So if you're only missing a few numbers, and they're exact numbers, if you're missing an interval, that's a problem. But if you're missing just one number, you can say all the numbers except that one number. Doesn't work. Okay. Hang on. Let's look at my y's. So my range, y equals which y values do not hit the graph? So I draw a line that goes through my y-axis. Do any of these miss? Everything from here down. So my range, what's my smallest y that counts? -5, comma. If that was the worst infinity ever. Does 5 count? Well, if it doesn't state it, it's always a yes. Okay, if you're unsure whether it's open or closed, it's always closed unless there's a little open circle. So closed and then open. Okay, what if we had something like is this a function? Yes, it passes the function rules. So let's look at the domain. Are there any x values, any vertical lines, that miss the graph? Right there? So on the left side, in this portion, what is the smallest x value? X value. 0 is the biggest x value. So the smallest is -infinity, and the biggest is 0. Do we count -infinity? No. Do we count 0? Yes. Okay. On the right portion, what is the smallest x value? 1, comma, infinity. Does 1 count? No. Does infinity count? No, it never counts. Okay? So let's look at the range. Y equals, how come I didn't say x doesn't equal 0.5? How many numbers are there in this little gap? An infinite number. Okay, that's a pretty small infinity though, right? You see how some infinities are bigger than others? Okay, for my ranges, I'll look at the top piece. What is the smallest y value on that top piece? 1. The lowest value is a 1. What's my highest value? Infinity. Does 1 count? Yes. Does infinity count? No. My second one, what is my smallest y value on that portion? Negative infinity. Does negative infinity count? No. What's the biggest number? Negative 1. Does negative 1 count? No, because it's an open circle. So that would be my domain and my range. All right. Your assignment is due on Monday. Wait, Monday. Today is. Let's Monday being tomorrow, which is actually Wednesday. Sorry, guys.